Alright guys, so today we're going to be talking about the change of base formula for logs. So I actually had this on a previous document for you, then we kind of skipped it and said we'd be coming back to it this coming week, so here we are, right? Log base b of a is equal to log base c of a over log base c of b. Now, you can change the base to anything you want, alright? It could be a natural log over natural log or common log over common log, but the inside expression or number is going to go on top and the base is going to be logged in the denominator. So now let's see why this is actually true. Okay, let's just run through this real quickly and then I'll show you a couple problems, okay? So we're going to take the log base b of a and we're going to set that equal to x. And that way, b to the x is equal to a, because this log equation is equivalent to this exponential equation. It's just written in a different form, right? And so then we take the top log here, log base c of a, and set that equal to h, and then the bottom log and set it equal to k, and you've got their exponential expressions here, right? So we need to manipulate these things in order to prove that one side is equal to the other. So here's how we do it. So since b to the x is equal to a, and we know b can be written as c to the k, and we know a can be written as c to the h, we can substitute that in for b and a, and we get the following expression. C to the k raised to the x power equals c to the h. We can simplify the exponent, that is multiply the two exponents there, and get c to the k times x equals c to the h. And since the bases are the same, we actually solve the equations like this. All we have to do is set the exponents equal to each other. So that's k times x equals h, k times x equals h. And when you solve for x, you get h over k. Well, now, since x is log base b of a, that's how we defined it, and h is log base c of a, we just substitute those things in, and boom, it's equal. So now, you might be saying this is rather unremarkable. This proof doesn't shed any kind of light on what it's used for or why it's important or anything, but it actually is kind of important for initially being able to calculate logs of various values. So for example, log base 2 of 50. Now I know that 2 to the 5th power is equal to 32. And that 2 to the 6th power is equal to 64. So there is some number in between 5 and 6, such that the log base 2 of 50 is going to be some exponent in between those two values, right? So how can we actually calculate this? Now I know I showed you on the calculator, the graphing calculator, that there is a log base, in the math kind of section. However, if you don't happen to have that or you can't seem to find it, we can always calculate this using, say, natural log. Put natural log of 50 over natural log of 2. That'll give you the value. That's a change of base formula, and we can use that in our calculator. Or, if you'd rather not use a natural log, you can always use the common log of 50 over the common log of 2. Does not matter which formula you get, and most calculators do have natural logs and common logs on them. So if we do log of 50 divided by log of 2, I get 5.6438 and it keeps on going because it's probably not a great number, but take that value now and raise 2 to that power. Go ahead and do 2 raised to the 5.64385, hit enter, and your value should be either 50 or super close to 50. I think I went out to this decimal point right here, the 385, and I got 49.9997.8. So it's pretty darn close to 50. Okay, so try that for number 2. Calculate the log base 4 of 70 using your calculator using a natural log and a common log. Okay, so if I did natural log of 70 divided by the natural log of 4, all right, on my calculator, natural log of 70 divided by natural log of 4 gives me 3.06464, and it keeps on going. Again, 4 to the third is 64, so just a little bit bigger than 3, and we have our exponent, okay? Now, this can help us solve some pretty weird problems, and there's not a problem like this on the homework, but I just wanted to show you that if we have 3 to the 2x plus 4 equals 7 to the 4x, now here you can't make the bases the same of this exponential equation. However, you can natural log both sides of the equation. So the natural log of 3 to the 2x plus 4 is equal to the natural log of 4x. The reason why these logs help you is that the property of logs, the power property, allows us to bring these exponents out front. So we get 2x plus 4 times the natural log of 3 equals 4x times the natural log of 7. All right, now natural log of 3 and natural log of 7, these are just decimals. These are just numbers, like these infinitely long decimals up here and everything like that, I'm sure. So like either you can turn them into a decimal here and then solve it, or what I'm going to do is I'm going to leave them in this form, and I'm going to distribute that natural log of 3. So I get 2 natural log of 3 times x plus 4 natural log of 3 is equal to 4 natural log of 7 times x. And so I'm going to subtract this 2 natural log of 3x over. So that will cancel out on this side. On the left-hand side, I'm going to factor out an x. 4 natural log of 3 is equal to 4 natural log of 7 minus 2 natural log of 3 times x, and I'm going to divide that over. And so I get x is equal to 4 natural log of 3 all over 4 natural log of 7 minus 2 natural log of 3. And if I plug that into a calculator, divided by 4 natural log of, is it 3? Yeah, 4 natural log of 3 divided by that, I come up with 0.7866312. Okay, if you try and plug that into the original equation, it should give you the same thing on both sides when you do that. And it does. All right. You can check that on your own. Plug in this decimal right here into the original equation for x on this side and kind of calculate that side, and then plug it in over here and calculate that side, and you will see they're the same. Okay, and so these are some using logs, natural logs, things like that to try and solve problems. The last one used an inverse type thing, taking the logs of both sides. We're going to do more of that when we start solving, when we continue solving next week. There is a weird question in the change of base problems, something like this that I just wanted to go over. 3 to the log base 3 of 6 minus log base 3 of 5. Now, I know if this was 3 to the log base 3, that they're going to undo each other, and I'm just going to get out whatever box is. Of course, that's as long as it's positive, right? But here we have two things. So what we're going to do is we're going to use the properties of exponents to kind of split them up. Subtracting exponents is the same thing as division. This is actually 3 log base 3 of 6 over 3 log base 3 of 5. Okay, so representing that subtraction of exponents and splitting it up like this now allows us to do these two inverses. The log base 3 of 3 raised to the log base 3 is just going to cancel out, leaving you 6 in the numerator. And 3 log base 3 of 5, the 3 to the power and the log base 3 will cancel out, giving you just 5. So your answer is 6/5, okay? Just be careful if there's any number that's in front of the log in the original expression. If there was any coefficient here, you could bring that up as an exponent. That's on the first log or the second log, so you might have to watch out for something like that. Other than that, should be able to do the change of base homework, and I'll see you for the next lesson. Thanks.